So let's start. This is a technical session, and we will be sharing this, me and Julieta. So my name is Thomas Pettersson. I'm a professor in drinking water engineering from Chalmers University in Sweden. So we will share this. Should you introduce?
Hello, everybody. Thank you for being here. My name is Julieta Lopez. I'm a professor at the engineering school, and I'm also the CEO of Fundación Ricaldoni.
Thank you. So then let's start. We have a lot of presentations now, and we have short of time, so we need to keep the time. We have 6 presentations, 3 normal presentations, 15 minutes, and also if there are questions, we can take them after. And then after the 3 normal presentations, we have 3 poster presentations, which are much shorter. It's just 5 minutes and not really room for questions if we don't have a lot of time in the end. So I think we should start as soon as possible. So then we introduce the first speaker, and it's Alba Cabrera from Spain. Alba is has a PhD and researcher at University of Girona in Spain, and she works in the Chemical Environmental Engineering Research Group. And the title here is Predicting THM Formation Potential with Rapid DOM Analysis into Drinking Water Treatment Plants. So please, Alba, the floor is yours.
For your introduction. Buenos días a todos. ¿Funciona bien esto? Sí. I need something for passing the slides.
Sorry, here it is.
This? Okay, thank you. I come from the University of Girona, as you said, from the Laboratory of Chemical and Environmental Engineering. This is a research group, quite big one, with 45 researchers. We cover a lot of environmental engineering topics, most of them for wastewater treatment, but recently, from 10 years ago, we started research on drinking water treatment, and we are doing a lot of work on this. So if you don't know, Girona is in Catalonia, in the north of Spain, and most of the research we are doing in drinking water, oops, I'm sorry, this is the good one, okay, is done covering all the region. We are working with many drinking water treatment plants. Starting from the north, we have Figueras, the yellow dot. Also in Girona, in this city that is in the orange dot. Also drinking water treatment plants that supply water to Barcelona, to the Barcelona metropolitan area, and also more in the south to Tarragona. And we also, I'm sorry, do I need push this all the time? No, it works. Okay. And also the supply network that distributes the water from the drinking water treatment plants to the consumers. The challenges that we are facing due to the global warming has been introduced this morning, and here we have an example of that we have in our area, in Girona. Here you see the pictures of a reservoir that is very particular in our area because there is a charge in the bottom of the reservoir that usually we don't see the top of this charge. It's usually covered by water, and we only see the top of this charge. But the last month we see the charge completely. So there is a lot of water scarcity. And also other challenges are due to different levels of contamination. So this is a very active research area in our group. Héctor Muclús is the principal investigator of this area. He's also giving a presentation tomorrow at this time here. And these are some projects that we have with funding from the Spanish ministry and also from companies that we are going to present today with these two presentations and tomorrow. So we know the Sustainable Development Goals that are to provide resilient, safe water to population, and to do so, we need to remove contaminants from water, including natural organic matter, which includes suspended solids, turbidity, color, and dissolved organic matter, and also to disinfect water to remove pathogens and microorganisms. And as we all know, the combination of natural organic matter as a precursor for the formation of disinfection byproducts and chlorine leads to the production of these toxic pollutants. So the aim of drinking water treatment plants is to provide this water. This is the conventional treatment train that the drinking water facilities that we have working with have. This is the treatment from these particular cases. The most conventional treatments we are using is a pre-oxidation with ozone or with potassium permanganate that aims to break the organic matter, to remove inorganic compounds or pathogens, and to improve the treatment efficiency in the subsequent technologies that are used. Then we have usually a coagulation flocculation plus sedimentation unit that aims to remove colloidal organic matter. This is followed by an activated carbon filtration unit that removes the soluble organic matter. And this is followed by the final disinfection that can be with or without radiation, with ultraviolet radiation or not. But the chlorine is mandatory in Spain. And with all this strain, the natural organic matter is removed to achieve a formation of trihalometanes that are the disinfection byproducts that are legislated under the 100 ppb limit. So in this context, the objective of the work I'm presenting now is to characterize well the composition of dissolved organic matter and understand its reactivity towards disinfection, to analyze, to predict the formation of disinfection byproduct in the distribution systems. To do so, we are using size exclusion chromatography coupled with diode rate and organic carbon detectors. But this is a complex methodology, so the outcomes of this technology for analyzing organic matter, we will try to simplify them with more bulk analysis methods that we can use online with rapid analysis with visible UV and with fluorescence detectors. And all of this, we will try to digitalize them to apply in the drinking water facilities. So this part I'm presenting now is part of the PhD thesis of Meritxell Valentí Quiroga. She is almost ready to defend the PhD this September. And what she's done is develop a method where she can characterize the organic matter based on the fractions according to the molecular weight. So using size exclusion chromatography, we can divide the natural organic matter in biopolymers, humic substances, building blocks, and low molecular acids and neutral compounds that also can be subdivided in fractions. And to do so, we are using two columns, chromatographic columns in series. And this is the separation method we are using. We have more details if you are interested in the analytical technology. And this work is carried out with three of the facilities I introduced you before. One of them is Abrera, which is they are all in Barcelona. That is treating water from Llobregat River, this one in the picture. Being a river with a lot of industrial protection, it has some bromides in the water source. Here you see, for instance, in the chromatographic separation, that there is a lot of building blocks in the fraction. in comparison with Cardedeu and Montfullà, which is in Girona actually, that the distribution of the fractions, they are quite different. What we did is analyze along the water treatment in the facility. Here you can see from the catchment to the coagulation, flocculation, adsorption, and the different technologies applied, how the different fractions are reduced. And what we can see, for instance, is that coagulation, flocculation have a lot of reduction in the reservoir sources, and in the river sources there is a different behavior, so adsorption produces a higher reduction of other fractions. If we compare from the influent to the effluent, how this chromatographic separation changes. Here you can see only the chromatograms, but this is something that needs to be observed in detail. So here I only put the influent and the effluent for comparison, but here you see the numbers. This is the talk of each fraction from one stage to the other of the treatment. The main changes are in the omic substances. And we also included here in bank scale, so testing in the laboratory, not in the whole facility, the reductions made using ion exchange resins. So we compare these reductions in the dissolved organic carbon with the same water reduction of the formation potentials of the trihalometanes. To analyze the formation potentials, we did some chlorination with 3 ppm of sodium hypochlorite, with analyzing them with gas chromatography with heat space. And we compared the reductions with the formation potentials. And here I show for the river water the Pearson correlations of the reduction in the organic matter with the increase of the formation potentials. And we see how the behavior depends on the organic fraction reductions and the type of water. For the river water, that is these correlations you can see here. This is humic substances of different types, and you see that the bigger the green dot is, the higher the correlation. And here the higher correlation are with the brominate species. And for the trichloromethane, that is the trihalomethane that doesn't have bromides, the correlation has very small green dots, meaning that there are not so many correlations because it is not the dominant species. Instead, on the contrary, for reservoir waters, the correlations with the brominated species are smaller, meaning that the behavior is very different between them. This may be complicated to understand here, but we have a couple of publications and we can see it in detail. But the idea is that depending on the type of water and the type of organic matter, we can predict what will happen. And what we want to do now, and what we are doing now, is translate of this information that we can obtain with size exclusion chromatography, that this is not an easy technique, with simplified bulk analysis. We have master students that are now starting their PhD and will work in improving coagulation, flocculation processes that are the ones that are removing more organic water, and also in improving the analytical techniques with fluorescent spectroscopy, that is a very promising technology, to translate the information of size exclusion chromatography to this online analysis. For instance, we have this sensor from SCAN that can analyze the whole spectra online, and also we have already this in some plants, and we will include a fluorescence sensor. That this is the one that we have in the laboratory. You know that some organic matter is fluorescent, and some regions of the organic matter will correlate with also some fractions of organic matter. So the idea will be to do the same prediction of the formation of disinfection byproducts with this analysis. We also see with the fluorescence how the treatment goes on, some fractions are reduced, and we are also obtaining, these are preliminary results, the correlation with the formation of trihalometanes with reductions in fluorescence and absorbance with some parameters. So the conclusions of this piece of work is that the natural organic matter compositions depends on the origin of the water sources, if it's from the rivers or from the reservoirs, and the technologies applied in the drinking water treatment plants target different fractions of the natural organic matter, that we can identify correlations between these fractions and that these fractions determined by size exclusion chromatography and trihalometanes formation potentials, and the information provided online by the bulk analysis should be able to correlate with the knowledge provided by the size exclusion chromatography. So this is the first part I wanted to present today.
Thank you very much. So let's see now, thank you. And are there any questions? Please raise your hand and clearly state the question. We have a question over there, and I think there will be a mic running here. Can you wait a second? So now.
Vi que, que hicieron una correlación de la materia orgánica natural en relación a la formación de los trihalometanos, ¿no? Y en particular algunas fuentes de agua tenían alta concentración de bromuro o concentración de bromuro. De la familia, digamos, o de los grupos de los subproductos de desinfección, además de los trihalometanos, están los ácidos alocéticos también, que son como las especies predominantes cuando se utiliza cloro como desinfectante. ¿Esa correlación la tienen pensada hacer? ¿Han visualizado eso? Porque, digamos, de los 9 ácidos acéticos hay unos cuantos bromados, ¿no? Por lo menos 6 son bromados.
Sí. En España los ácidos alocéticos no están regulados todavía. Existe previsión, hace tiempo que se escucha que se van a regular. Eso por un lado. Sobre todo no están regulados porque son mucho más difíciles de analizar, pero los hemos analizado en varias de las estaciones de tratamiento con las que trabajamos y están a concentraciones muy, muy bajas. Y no parecen tan problemáticos a nivel de concentraciones, aunque sean tóxicos. En nuestras aguas no los hay o lo están a concentraciones muy, muy bajas, a pesar de las plantas que tienen bromuros. Por lo tanto, de momento, aunque tenemos en mente, como me preguntabas, empezar a trabajar con ellos, no parecen, igual están a un 10% de la concentración a la que están los trihalometanos. Pero sí, siempre es como el siguiente paso.
Bien, gracias.
Sí, gracias por la pregunta.
So, thank you. Are there more questions? There is time for one short. No? So you won't leave us, you will stay here because you have the next presentation. So I think you can prepare for that. And the title of your next presentation, Alba, is Development of a Predictive Physiologic Model for Controlling the Ozone Dose Rate in a Drinking Water Treatment Plant. And when I'm speaking now, I can also encourage you to not speak too fast when you ask questions or we are talking here or presenters, so the translator have a chance to translate everything. Just a reminder. I try to think on that myself.
I'll try.
So the floor is yours, Alba, please.
Thank you. Okay, so next, continuing with the same, I have cut the introduction a lot, of course, and this part of what I work was carried out or is being carried out by Laura Ferrandez. She is a PhD student with an industrial program with a drinking water treatment plant from Figueres, the one more in the north. So it's an industrial program to optimize the ozonization unit in this drinking water treatment plant that is very well, it's quite unique because it has a lot of technologies. It has a ozonization pre-unit and also ultraviolet disinfection unit at the end. So they want to optimize the treatment because if they use everything at full power, it's an expensive treatment. So they are very interested in optimizing the both ozonization and UV. But it's drinking water that treats water from Darnius-Boadella Reservoir. It supplies water to 60,000 inhabitants with a maximum treatment capacity of 0.25 cubic meter per second. And yeah, this is the unit they want to optimize. So chlorine is mandatory in Spain, and well, you know, it may lead to the generation of disinfection byproducts, and ozone is a proposed alternative or complement treatment to reduce the formation of disinfection byproducts. It also can be used for other applications as pre-oxidant, and it has many benefits. It helps to remove color, odor, and taste compounds for the abatement of micropollutants and the removal of inorganic compounds. And it oxidizes and reacts with natural organic matter, improving the efficiency of the treatment, but it has some limitations. It needs to be produced in situ, which is expensive, of course, because it's an unstable molecule that have short life, and the incomplete mineralization of organic matter leads to the generation of other disinfection byproducts. So using it as a pre-oxidation step increases the polarity and the hydrophilicity of dissolved organic carbon and decreases the number of double bonds and the molecular weight. What happens is that it can increase the biodegradability of organic matter, making it more suitable for microbial regrowth, what we call assimilable organic carbon. This is something that we are studying because limitation can be that we can make it more easy for bacteria to regrow by the organic matter breakdown. So, well, you know from the previous presentation that we can evaluate the changes on organic matter that we are producing by some bulk analysis, including the absorbance, the fluorescence, and also by the size exclusion chromatography. So, taking into account the changes we know from the global warming, the need for quality and in the water provided, and the need for safe water, the changes in the quantity available, all of this is a complex system we need to manage, and this is why we want to develop an environmental decision support system for the water facilities to manage the water supply. So this environmental decision support system we want to develop comes with several stages. The first one is the problem analysis. In this step, we need to analyze the problem of water quality, of the cost, the energy consumption. Following, we need to see what is the data that we have, the data that we can provide the system with, if it's online data, if it's data from the laboratory, the cognitive problem analysis that need to fit the model, and what type of machine learning model we will use. And finally, the integration and validation of this model. The models are, the model we will develop has this geometry, this pyramidal geometry, that in the first level has the data acquisition. This is where the drinking water treatment plant feeds the model, and the data is filtered and processed. In the diagnosis level, the actions are proposed, and in the supervisor level is where these actions proposed are controlled and validated. So the results obtained in this environmental decision support system are developed in the MATLAB software using a fuzzy interface, and the final output was the ozone dose predicted using as inputs the absorbance of the water and the temperature of the water. To arrive here, I'll try to explain why and how Laura did that. And to start with the parameters we choose as inputs from the ones we had available. The first one was the absorbance at 254. We all know that this correlates very well with organic matter concentration. The higher the ozone dose, the higher the removal of organic matter, so the absorbance. And this was the first parameter in the data acquisition level that was selected. And the other one was the temperature, because of course temperature is related with the ozone solubility, and ozone is a gas, so temperature was a critical parameter. So these one are the two parameters that are introduced in the data acquisition level. Secondly, the diagnosis was proceed with the fuzzy system, that what does is transform numerical to linguistic levels and then again to numerical. To do so, the numbers from temperature and absorbance are transformed to be categorized into low, medium, or high values of temperature and absorbance. When the data is classified, then it can be again transformed into the graph we saw before that can give an output of the ozone dose required as function of these two inputs. So when the plant started applying the model, here you can see in the dashed vertical line before and after the actual ozone supply. This is the red line. I'm saying it well? Yes. The real ozone supplied is the red line, and the predicted by the model is the black one. So after using the model, after the dashed line, the ozone consumption was dropped 30%, so the energy consumption was dropped 14%. And this was validated using the scan sensor used before. And accordingly, the trihalometanes were also dropped. This is the interface of the environmental decision support system they are using in the plant. So this is the supervision level, and some inputs can be changed according to the user, so the user can interact with the model using this interface. Tomorrow in Hector's presentation, he will show more about this platform, because we are using this in other drinking water treatment plants for the other purposes. And this is, we have several ways to improve the system. Now it's working in a feedback system, so that the system works according to the outputs. But in order to improve it, we want to update it with a feed-forward system, so the data can be corrected. And also, we want to improve it using the fluorescence data that I told before. So this will be another improvement that we are working on. And as conclusions, we can say that the ozone consumption was decreased after the implementation of the FUSI-based environmental decision support system, that the model is being validated with online and will be expanded, that the natural organic matter characterization by advanced techniques will predict or predicts the trial meta information, and all the information will be included in the environmental decision support system, combining it in a closed loop. So,
Thank you very much, Alba, for the interesting presentation. So let's see if we have any questions here in the audience. I have a question first. If you go back to the slide where you have the dose and of the dashed line you had. That one, yeah. So you had the real dose, and then you have the predicted dose. So this was how you worked until you implemented the decision support, and then you backtrack and check what should it have been.
Yeah.
Yeah. So how much did the water producer save in ozone dose? Did you say that?
So before the line, we ran the model, and what you said, what the model would have said if it was applied before. I'm sorry. So the question was?
The question is how much less ozone do the water producer use now when they not overdose?
Yeah, so after the model, the user did what the model said, and after the model, before the model, they were doing that amount.
Yeah. So it says 30% here. Is that an average?
An average, yeah. Because in some cases there is much more than 30%, you're right.
So will this also imply that the byproduct formation is also lower?
Yes, it goes from 25.4 to 22.3. This is also averages.
I see that now. Thank you. Thank you. Okay, let's see if there are more questions. We have questions over there. Philip?
Thank you. A similar question to Thomas. So I was just thinking, you're obviously playing around with the model, and for a utility to implement it, hopefully that's the idea. What do you think, in terms of, we're talking about energy consumption savings, what do you think the investment cost would be for them to implement it versus the savings? Because then, it's quick for them to make that decision if it's a low investment cost. So that's the first question. And then the second question is, do you see this also potentially being applied at the design stage of a water treatment plant? Or, do you think engineers are still going to be worried about over-designing a water treatment plant and not optimizing that design from the start? Thanks.
Yeah, maybe Hector wanted to help me. I don't know, some of the drinking water treatment plants, I would say they are working very close with research institutes, so they are taking our advice very seriously in the design processes. And the ones that are being, they are all constructed, but the ones that are somehow being expanded are considering the research work seriously, so they are taking this into account. Hopefully they will hear us. And sí. You want mine? No, sí, Dios.
So only to complement the answer of Alba. The tool is already installed in the facilities, so they are already using. It's true that we are in the validation process that can length as they want. So as more data, better for us, because the model can be adjusted perfectly, better. And another thing is the tool is not only for a real-time control, so it's like a simulation, a scenario simulation, evaluation, new weeks of different events like storms, like different events periods, scarcity or whatever. No? So at the end they have a tool in order to evaluate the real process in real time, and also they evaluate the future events in order to evaluate if their treatment are able to treat the next water that is coming. And I think that's all. Okay.
Thank you. Thank you very much, Alba, for a two nice presentations. So give you a big applause again.
And now we invite Javier Medina to join us.
Okay.
Well, Javier holds a degree in chemical engineering. He also has a master's in financing and infrastructure and also in business administration. He's particularly passionate about remote data monitoring and sensor integration, dedicating his effort to incorporate these technologies into operational procedures and management systems, as he says. He serves as the Chief of Sanitary Control and Development at OCE and has more than 15 years of expertise in water quality control. Thank you, Javier, for being here. And his presentation name is Real-Time Monitoring and Modeling for Sustainable Water Management, a Response to Drought in Uruguay.
Well, good morning, everyone. For the next 15 minutes, we will be talking about how drought and information system based on real-time monitoring was used in the context of the water crisis we had in 2023. First, we'll start with a brief outline of the presentation. We have an introduction, then we frame the crisis, and we discuss 3 challenges and how we solve them. Then we will have the conclusion, and we'll talk a little bit about what we are doing right now. Finally, hopefully, we have some questions from the public. So we work at the Sanitation Control and Development Department within the metropolitan area. Our department is responsible for addressing quality-related problems, mainly customer complaints. We also do some monitor, either by manual sampling and remote sensing. We also help with compliance, yes, and also do some automation projects. So, to begin with our analysis of the crisis, I will present you the Santa Lucia River Basin that is about 5,000 square miles, and it plays a crucial role in supplying water to the capital city. It serves as the primary source of water for about 60% of Uruguayan population. The Aguas Corrientes treatment plant started operating in July 1871, so we have a long operating history. I must state that during this time we have not encountered a drought of this magnitude. About the plant, it's a conventional multi-stage treatment process. It has a capacity of around 650,000 cubic meters per day. And for this structure, it has 4 raw water intakes, and the coagulation, flocculation, and sedimentation processes is divided in 2 sectors that we call them Planta Nueva, what is about 200 cubic meters per hour, and Planta Vieja, that is about 25,000 cubic meters per hour. So, what was happening in 2023? Well, we experienced the third consecutive year of below average rainfall. We also have almost no significant precipitation between October 2022 and August 2023. So back then, the question was, what was the best way to protect the population? At that time, we had many available options that were insufficient to meet the demand. We could drill some wells, we could try to borrow water from another system, but bringing the water would imply like around 21,000 trucks per day. So that options were available, but just for use in very specific cases. So in general, we have two options. Just to go to severe rationing the water supply, or use brackish water from downstream. While we have some experience using brackish water from downstream, because we do it limited on hammers, in this situation we would need much more water. We would need more pumps, bigger pumps, and also to mitigate the impact of the tidal fluctuations, from downstream, we would also need to build a dam to create a reservoir. At that time, that is around February 2023, the team of the treatment plan was working hard and very diligently to procure and install the pumps. Later on, a dam was built. But even though all the efforts we have made, we knew that the supplied water will be increasingly saltier. Actually, I want to also state that many other things were done, but out of the scope of the presentation. So that's our bottom line. We wanted to ensure that the population was not exposed to levels that pose a risk to the health, and also prioritize the provision of clean water for the most vulnerable populations. So here we will start to discuss things we've done to solve 3 different problems using the same methodology. At stage 1, that was at the very beginning, we wanted to keep track of the sodium chloride levels, of the intake levels of the population. At the stage 2, that is when afterwards, we wanted to help the plant operators in the operation management, and also this tool at stage 3 was a viable tool to communicate with the community. So, how to track sodium and chloride levels of the cell population? Well, we need a sampling plan. For a sampling plan, we need to define a sampling strategy, define the frequency, define where, and define the weighting function. So, one of the measure decision was choosing between the sample strategy. We could use manual sampling, that is the traditional way, and it's very precise. It gives us but it gives us punctual data. It also we also have some logistic concerns, and especially, I think this was a major drawback, it's extensive in human resources. We have to think that back then, the personnel we have was already overwhelmed with all of the duties that were coming to the office. On the other side, we have the online analytical instrumentation, but the problem here is we didn't measure chlorine and sodium. However, and that was part of the solution, we can measure conductivity as a proxy. We have a measurement that is highly stable, and we know we already have some conductimeters installed in the main lines, and we can add more if needed. And what is more, it works tirelessly, 24 hours a day. So that's how we solve the sampling plan problem. And I would say we can measure the conductivity in the main lines every 30 seconds, average the results in 24-hour period, and estimate the average levels on sodium and chloride to generate a report every day so that the decision maker can do their work. In the pictures, I'm showing the first report we made that was in 16th of February 2023. At that time, the report, we extract the data from the SCADA system and process it in a spreadsheet. Later on, we improve the model and automate it. Well, here, at this point, I think it's valuable to give an insight of the structure of our data collection and information system. On the left, we have an actual data acquisition station that is close to one of the main lines. Then I have a scheme of the communication structure. We have some, well, we use private networks and public networks and so communication protocols to send the data to the SCADA. From the SCADA, we have some databases that we use to produce the reports. So at stage 2, there was a new problem to solve. At that time, the transfer pump started operating, but the sodium chloride levels were changing too much, and it was difficult for the plant operators to adhere to the operational guidelines. Why? Well, aside from the lack of water, there were several process-related factors that contributed to the issue. First of all, the transfer pump operates on and off, and the output of the pump were much closer to some of the intakes of the treatment plant. Also, as the process is divided in 2 sectors, we have different retention time for the water within the treatment plant. Also, we have to take into account that the retention time in the plant is about 6 to 8 hours. So, the question now is how to get more stable and more stable sodium and chloride levels. Well, we need to find a way to predict the output. So we have to install some conductimeters, find a suitable model, calibrate the model, and add the model to the SCADA. And that's what we did. We installed some conductimeter with communication equipment. Then we make a model, make the calibration, and then integrated the output to the SCADA. That is an actual picture of the SCADA for staff access. Okay. Yeah. This is the conductivity profile of the output, 1 month apart, one before and one after. But because it's difficult to make a comparison because the conductivity have changed, we superimpose the curves. This is not proof of the absolute value nor the solution of the improvement, but I think it helped. So as Proverbs said, never 2 without 3, and at that moment we were approaching the most challenging phase of the crisis, and the humans were highly concerned about the water quality. So, and that time, some clever individuals sized our report and used this information to quantify the problem, thus providing a measure and metric to inform the population about the situation. At that time, this information was published in the webpage of the presidency, and then you will see the information in all the TV news and in radio, newspaper, etc. So, as a conclusion, during the crisis, the control strategy has to adapt to the new circumstances. Remote sensing and data acquisition proved an excellent tool not only to monitor but to help the production process, and it also provides the basic framework to communicate with the population. So this is a list of things what we are doing right now that is related to the example we just discussed. We are trying to incorporate some learning lessons to the water safety plan and further improve some strategies to distribute potable water. Also, we are working to further improve the information management system. We want to put in production a better warehousing model, so we can utilize different database sources. And from the online monitoring system, we want to implement an upstream monitoring station, improve the treatment plant instrumentation, and also we are working in improving the measuring system. So before concluding this presentation, I would like to acknowledge the individuals who were instrumental to the success of the story, and would like to express my gratitude to my team members that their hard work and creativity were very important for this project. So please, thank you very much, and feel free to ask some questions.
Thank you, Javier. Do we have any questions over there?
Hello, thank you for the presentation. I wanted to ask you first, in what moment did you make that decision of taking brackish water? When do you stop and said, well, we have to make a decision?
The moment we start with the report.
What time?
I would say 15th of February.
Okay. And the other question is about the sampling strategy, that you mentioned that you choose the online strategy, but I wanted to know if the manual sampling strategy or measurements were used to calibrate the online strategy.
Oh, we calibrated with the microphone. Oh, sorry. To calibrate the response, we use data from manual sampling.
Okay,
and we
perfect.
measure sodium chloride, and we relate the variables.
Thank you.
Any other questions? Okay, thank you, Javier. Over there. Sorry, Philippe.
Thank you. Great presentation. Obviously, the city of Cape Town had similar issues with drought. Have you seen after, if the drought is now over, or if you consider it to be over, have you seen public's perception changing over the role that you have played? Like in terms of communication, you were proactively communicating to the public about the quality. Do you think that they trust you more now, that if there was a problem, we would let them know? Have you seen an improvement in the engagement with the community going forward, in essence?
I think I don't have the information to answer your question. What I would say that when this information starts to be published, the public, we have the people who's talking to the public and responding the complaints. And at the beginning, or at the time where the water was salty, it started to get really salty, they were really angry with us. And these simple things help to calm them down. Yeah.
Okay, thank you very much, Javier.
Well, thank you.
And now we invite Pablo Koch for our first poster presentation. Pablo Koch is a civil engineer from Uruguay with a master's in sanitary engineering from the Delft Institute in the Netherlands. He works at the Ministry of Environment in activities that are related to water resource management and water quality assessment. And he is also a professor at UTEC University at the Water and Sustainable Development Program. And his poster, you have the title over there. is Bridging River Basin Models and Water Safety Plans, an Approach in Uruguay. Thank you, Pablo.
Thank you. Hello, everyone. Well, I will be brief here, presenting this work named As You See. And the basic of this work is to integrate and to work together these two approaches related to different type of tools and some of the work we do in the Ministry of Environment. We work in the Ministry of Environment with water quality modeling at a basin scale, and there we see many interactions at a basin scale and decisions that are made at a catchment level. And these tools has different type of uses. They systematically incorporate many amount of data related different aspects, soil use, climate information, water quality information, and there we get to some results that integrates all the dynamics into a basin. Then on the other hand, we have the water safety plans that are developed by other institutions. In this case, is developed by OCE, URSE, and they take care of that. And typically, when you look at a water safety plan, you have different subsystems that you analyze. And there is the first subsystems related to source is very related to the basin and to the catchment that you have before, if it has a surface intake. So this work that I have some time spare outside if you want to share some ideas and to see the results related to this work. Basically, types of link these two aspects. When we go for a basin scale in our country, typically the problems are more in water quality are more related to nutrient loads and eutrophication of water bodies, and this also has generates some problems that are identified in the water safety plans. So when we look at some examples, we can see that in water safety plans, some of the risks that are assessed are related to discharges associated to agricultural activities, also runoff from agricultural and excess of nutrient that can be delivered from soil to water, and also some events of algal blooms that produces some problems in the drinking water production. So on the right side, we see some of the examples of outputs we can see from the water quality models. And in this case, we show an example of frequencies of total phosphorus that we see in different seasons. And when we look at that, we can associate that some of the decisions that we take in a water treatment production, in a drinking water production, can be related to this type of outputs and to decide different type of options in your treatment. So this work that basically goes in this direction, and I would be happy to discuss outside. The general conclusions are that there are two tools that are can be very well linkages, very good linkages, and potentially they can help to make more efficient the two type of approaches. Then we also see that typically this type of developments are done by different institutions. So there is an opportunity to make some work together with the teams from different institutions, and this working tables need to be created. And there is also a need to create some integrated management tools and instruments for the water systems. So it's also an opportunity to work on that direction together in the different institutions. So here, that's all.
Thank you, Pablo.
So, post the presentations, we don't have time for questions, man. As was said here by Javier, we can meet them at the stand where the posters are. So let's go to the Pablo, sorry. Go to the next. That's Florencia Hastings. And you will talk about assessing water quality in an agricultural catchment, insight and strategies for sustainable land use management. And Florencia, she's a hydrological and water quality modeling specialist, currently a consultant at the National Directorate of Environmental Quality and Assessment within the Uruguay Environmental Ministry. So please, the floor is yours.
Hello everybody, my name is Florencia Hastings and today I'll be presenting our work on assessing water quality in the San Salvador Basin with a focus on insights and strategies for sustainable and land use management. The San Salvador Basin covers an area of 2,000 square kilometers. The main city is Dolores City, okay. And the main river is San Salvador that runs northwesterly. Dolores City, the San Salvador River serves as the primary water source for the city. This study area is mainly characterized by rain-fed cropland, native grassland with grazing, and to a lesser extent, production forest. Additionally, there is intensive livestock production, including fattening farms and dairies. In these basins, nutrient pollution in water has become a significant concern due to these activities. Our research aims to identify these pollution sources and to develop strategies to manage and mitigate its impact effectively. Okay. To address these challenges, we employ a soil and water assessment tool, or SWAT, to simulate runoff, pollutant delivery, and overall water quality in the basin. We use an extensive data set, including local climate data, topography, soil properties, land use patterns, crop rotations, and management practices. The model was calibrated and validated using both hard data, such as water discharge, and soft data, including crop yield, biomass, sediment, and nutrient yields. Our calibration and validation results shows that had a good agreement between observed and simulated data, and indicates that the model can reliably replicate the flow and nutrient dynamics of the river. Our findings reveal that nutrient loads consistently exceed target thresholds across all flow conditions, where cropland has a big impact on high to moist flows, and then livestock and point sources had an importance in mid to low flows. These results improves our understanding of the complex relationship between land use, hydrological dynamics, and water quality in the basin. And this study offers a valuable tool for scenario modeling and supports the planning and management of natural resources in the San Salvador River. The SWAT model we have implemented is freely available and can be used for further research and for developing strategies aimed at improving water quality and promoting sustainable land use management in similar agricultural catchments. I invite you to visit the poster after lunch. We will be delighted to discuss our work in more detail and explore potential collaborations. Thank you.
Thank you very much, Florencia. We continue with the last presentation, poster presentation. It's a mitigation groundwater contamination from leaking sewer lines using optimized hot water injection that we will hear about. And sorry. Rashib, you are very welcome, and you are at the Department of Civil Engineering at IIT in north of India, and you're working with groundwater and also computational hydraulics and climate change. So please, the floor is yours.
Thank you very much, and good afternoon, everyone. So I will briefly present. So this is a work done by my student, PhD student. It's a part of that, as a part of PhD research, he did it. So idea is that that if your groundwater is contaminated by virus, then first is that how to manage that one. Okay, so some idea has been placed here. It's purely hypothetical, and further research is required. Okay, so that I'm going to present here. So I'm not telling much about that groundwater contamination by virus. So there are a lot of research work already done, and many people have reported that one, that groundwater in many parts has been contaminated by viruses. Okay, so this is just basically I have shown, and this is some data basically. So that almost 8% disease is caused by the consumption of groundwater, contaminated groundwater by virus. So the virus, when it comes, actually it has two part basically. One is the protein coating and the DNA RNA, and both are required for survival of the virus. And then they are highly sensitive to the environment they have basically, or the temperature they have. So we actually took that idea, and then how to manage these viruses. So now basically, so as I said that these viruses are very sensitive to temperature, pH value, and solution chemistry. So by changing those things, if you can change that one, the temperature if you can change, or the pH value you can change in the medium, so virus can be eliminated from the aquifer. So in this case, I have used the temperature. Suppose if you can change the temperature of the medium, and then you can actually decontaminate the aquifer medium. So this is basically some of the research already done, because I am not exactly working on this part, that how virus is sensitive to your temperature and basically that one. So with the increase in temperature, so what will happen? So there are, suppose I can model this thing using the advection diffusion equation, but in this case, what will happen? There is a inactivation terms. At the inactivation terms I have shown here, and this is basically basically that how it will change. So inactivation will change with the temperature, and similarly sorption will also change with the temperature. So these two parameters we can change by changing the temperature of the medium. So now question is that what are the decision we have to take? So decision is that how to increase the temperature of the medium. So in this case, what we did basically that if we inject hot water into the aquifer through some injection well, and then aquifer medium can be increased temporarily. And if you stop it, then aquifer temperature will come again to the original level. So now what is the decision to be taken? Decision to be taken, what are the location of the hot water injection well, then amount of water to be injected into the aquifer, and duration of the injection, that how long you will do that. And for that, we develop a model, and this is basically, we use the ModFlow, we use RT3DMS, and we use MT3DMS. So this is the flow chart of the model. So finally, using that, and this is the basically the hypothetical problem that we have considered, and we have shown the injection well, and we have shown the observation well, and we have shown the contaminated source basically, and that has been obtained through an inverse model, and finally, this is basically the idea how we can select the injection well. Because I don't have much time here, so to explain that one, and basically, so we can select the optimal location of the injection well through that we can inject the water, and this is the result of those simulation optimization model, and here we have shown the heat map, and temperature will increase into the aquifer, and this is shown the Pareto optimal fawn for different level of threshold contamination. And this is basically showing, this particular map is, diagram is showing that if you are not doing anything, so this is basically the results of the virus, how it is spreading into the aquifer, and with these measures, actually, we can reduce the concentration of virus, and certainly if we go for some more time, that entire virus can be eliminated from the aquifer. So this is some of the results about this one anyway, so we don't have much time, and this is the conclusion of this. So we have developed a methodology for taking some decision to inject hot water into the aquifer, and which will increase the temperature, and finally we can eliminate the virus. Thank you very much. Thank you.
Thank you. So by that, I would like to close this technical session, and once again encourage you to have a look at the 3 posters that have been presented here today by Pablo, Florencia, and Rajib here. So please do that.